Carlos Plain, an educator from Durham School, shares his thoughts. Then, something unexpected happens to me after I've spent my entire career investigating bold theories about the universe. Our ideas are being scrutinized. I welcome this challenge, because it's through such questioning that we progress and make advancements in science. The James Webb Space Telescope is shaking up some long-standing beliefs in cosmology that we once thought were set in stone. A new set of high-resolution images has revealed mistakes we've made in our understanding of space. The telescope, originally intended to reveal the core stars of the universe, has ended up being quite groundbreaking. A completely new way of thinking might emerge from this fresh perspective. These new findings don't worry every scientist. Many are actually excited about them. After all, it's been clear for some time that our previous models had flaws. Experts ought to have been alerted long ago to the strange anomalies in our perception of the universe's expansion. However, many simply stuck to out-of-date theories rather than responding to those alarms. The cosmic microwave background, CMB radiation, the oldest light we can observe in the universe, was created around 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to form stable hydrogen atoms. This event, known as ionization, made the universe transparent to light. The CMB was first detected in 1964 by American physicists Arno Penzias and Robert Wilson, who stumbled upon a persistent noise while working with new radio equipment. At first, this discovery was seen as solid proof for the Big Bang theory. Penzias and Wilson were awarded the Nobel Prize, and their findings became a cornerstone in the history of space science. The CMB provides a snapshot of the early universe, offering tiny temperature variations that give us crucial clues about the conditions right after the Big Bang. The universe's expansion rate and other large-scale structures have been studied, using the CMB as a reliable marker. This idea was first proposed by Edwin Hubble in the 1920s when he observed that distant galaxies were moving away from us, with their speed correlating to their distance, a relationship known as Hubble's law. Although not as precise as current measurements, the initial estimates made by Hubble were groundbreaking. Scientists recalculated the universe's expansion rate following the discovery of the CMB and discovered that it was lower than Hubble's initial calculations. Later revisions, using type Ia supernovae as a reference, gave a more accurate estimate, but discrepancies remained. These differences in measuring the expansion rate, known as the S8 tension or Hubble tension, suggest that our understanding of the universe's expansion might be fundamentally flawed. The extraordinary data provided by the James Webb Space Telescope, JWST, since it began its mission, may help explain these inconsistencies. Some of the galaxies Webb has observed are so ancient that their formation might have occurred before the Big Bang, challenging current theories. Cosmology now faces one of its biggest crises yet: the rate at which the universe is expanding, and our theories about how everything began are under intense scrutiny. New images show a universe that appears vastly different from the models we once held. The S8 tension has acted as an early warning to experts who still cling to old hypotheses. Now, confronting the reality that our understanding of the universe may be incomplete, this uncertainty has left many researchers disheartened. To address this challenge, we need to understand how science works. To arrive at their conclusions, scientists make use of mathematical models, observational data, and logical reasoning. Their insights come from noticing unexpected results in experiments and rethinking old theories. The very word theory implies that concepts are always changing rather than being static facts. Our knowledge comes from images provided by telescopes, sound waves, and radiation captured by radio telescopes, as well as data from neutrino and gravitational wave detectors. The James Webb Space Telescope allows us to break down light into different frequencies and analyze it in stunning detail. It can reveal the composition of ancient galaxies, their mass, and the number of stars within them. However, Webb's images aren't without limitations. For example, it can't detect galaxies or black holes that appear bright due to gravitational lensing. Our comprehension has advanced to the point where we can consider alternative explanations, as these new discoveries sometimes challenge traditional models. These revelations are so groundbreaking that finding new explanations is proving difficult. These latest findings are rattling the foundations of physical science, causing concern among many experts. The laws of physics, as we understand them today, are still based largely on the work of Isaac Newton from the 17th century. His laws of motion and gravity have been the foundation of our knowledge of the world and the universe for centuries. Newton's laws work well in ordinary conditions on Earth, but in space, his ideas needed significant refinement. The early 20th century publication of Albert Einstein's theory of relativity advanced our understanding of gravity and motion by demonstrating that the observer's movement influences the laws of physics. His general theory of relativity, published in 1915, added the concept of curved space-time, which explains how mass, like that of stars or galaxies, bends the fabric of space-time itself. Although many of Einstein's theories have been demonstrated, he acknowledged their limitations and sought a unified theory that could connect everything. To this day, no scientist has fully succeeded in this endeavor. It's fascinating to wonder where the gaps in our knowledge lie. Physicist Miyawaku has even suggested that solving this mystery might lead to a Nobel Prize. We must investigate whether our telescopes are to blame or whether we have misinterpreted certain phenomena. Dark matter and dark energy are prime suspects in this cosmological crisis. Dark energy and dark matter, according to current models, account for approximately 95% of the universe. Neither of these has been directly detected, and we still don't fully understand their nature. They might not exist at all, or they may have properties we haven't yet discovered. One possibility being explored is that dark matter might have evolved over time, perhaps influencing gravity in ways we don't yet grasp. Gravity itself hasn't been definitively proven to act in the way we expect in all conditions. However, Einstein's idea of curvature in space and time has been repeatedly confirmed. We can't completely rule out the possibility that gravity has extraordinary properties or that some other unknown factor is influencing gravitational interactions. Some cosmological constants have been considered unchanging, recognized for their consistency over time. Small variations in these constants, however, might offer valuable insights into the universe, possibly helping to explain some of the anomalies we've encountered without dark energy. Additionally, it is possible that our understanding of how light travels through space is flawed, resulting in incorrect estimations of cosmic structures' age and distance. It's possible that we misunderstood the cosmic microwave background radiation, or that our assumptions about the conditions of the early universe were incorrect. It's possible that the universe didn't start with a single explosion like the Big Bang. Minor mistakes in the Webb telescope or other observation tools can't be ruled out. Some scientists acknowledge that errors in instruments, data analysis, or interpretation are always a possibility. The continuous reassessment of cosmological theories is a key part of the scientific method, being open to revising our understanding based on new evidence. The observations made by the James Webb Space Telescope are more than just a technological leap. They represent a monumental step in our journey to uncover the universe's secrets. As we process these new discoveries, it's important to keep the bigger picture in mind. The need to refine our hypotheses in light of new findings is what drives scientific progress. Unexpected anomalies in established theories can be unsettling to discover, but they also present a crucial opportunity for growth and discovery. Theories in cosmology are designed to provide a framework for understanding the origins, development, and future of the universe. However, as new data emerges, these models must be tested and, if necessary, reimagined to incorporate these fresh insights. One area of focus is the mystery of dark matter and dark energy, which play a central role in modern cosmology. Dark matter, a form of matter that doesn't interact with light, was proposed to explain the discrepancies between observed galaxy rotations and the mass that could be accounted for by visible matter alone. Dark energy was introduced to explain the observed accelerated expansion of the universe. However, despite their central roles in current models, dark matter and dark energy remain elusive, with researchers on Earth yet to definitively detect either one. Alternative explanations and theories have been investigated in response to this. The challenge of understanding dark matter and dark energy is intensified by the vastness of the universe and the difficulty of observing distant galaxies. The cosmic microwave background radiation and other key features offer indirect evidence of these components, but their subtle nature makes them hard to pin down. This uncertainty has led researchers to propose a variety of theories, from tweaks to current models to entirely new laws of physics. Some ideas suggest that dark matter could be composed of more exotic particles than we previously imagined, or that dark energy might represent an entirely new force of nature. Cosmic inflation, which suggests that the universe experienced rapid expansion in its earliest stages, is another intriguing area of research. While this theory helps explain the large-scale structure we see today, it also raises questions about the details of this inflationary period. It's possible that the early universe's history will need to be completely rethought if any new observations challenge our understanding of inflation. Finally, space exploration is still being driven forward by the search for extraterrestrial life. The search for exoplanets, planets orbiting stars outside our solar system, has opened up new avenues for investigating the conditions that could support life. Advances in telescope technology, like the James Webb Space Telescope, enable us to explore the atmospheres of these planets for signs of life. The discovery of life beyond Earth would have profound implications for how we view the universe and our place within it. In conclusion, revisiting cosmological theories is a testament to the power of the scientific method. The James Webb Space Telescope and other cutting-edge instruments have provided awe-inspiring insights into the universe, forcing researchers to rethink and refine old models. This ongoing process of inquiry, questioning, and correction is essential for expanding our understanding of the universe and addressing the big questions at the heart of cosmology and space science. As we continue to explore the cosmos, we remain committed to a quest for knowledge that not only aims to answer fundamental questions but also inspires future generations to challenge the limits of human understanding.